Hello, this is the second video in a two-part tutorial on ZIVA materials. In this scene I've got a couple of primitive objects. Here it's two bones and a tissue, and hopefully these objects are going to highlight the differences between different types of volume conservation in ZIVA. So if I play this back, what you're going to see is this tissue is going to end up sandwiched between these two bone objects. So I'll just play this back now. I'm going to play around 20 frames just so that the tissue squished in between the two objects can settle a little bit. And I'll stop that there. And so if we look in the material node here, you're going to notice that under Young's modulus, which you remember from the last video was to do with stiffness, we've got three extra channels here. So one of which is Poisson's ratio, and the default value is 0.4, and this takes a float between 0 and 0.499. So 0.5 is the theoretical maximum for Poisson's ratio, and that's a mathematical limitation on how the volume's computed using this method. So you notice that volume conservation is split into two attributes, just like Young's modulus, or strength on fibers, or stiffness on attachments. And by default, this value multiplies out to be 0. So a couple of things to note at this point. First of all, I've got a cache in the scene so I can scrub the timeline. If we use Maya to tell us the volume of this object, there's a command called compute polyset volume. It's just a standard Maya command. You can see that it's 545 units cubed. And if we go down to frame 20, and I run this command again with that object selected, you're going to see that it's all the way down to 410 units cubed. So that's quite a significant volume loss once the tissue is being compressed like that. If I were to set Poisson's ratio to its theoretical maximum of 0.499, I think is as high as you can set this, and clear the cache and play this back again. Under some circumstances, the closer that you get to 0.5, the more unstable the system is likely to be. So if you're going to use Poisson's ratio, you probably want to stick with a value of about 0.4, I think is kind of safe. So if I scrub this down now and go to frame 20, and then I run compute polyset volume again, you're going to see it preserved a bit more volume, but we're still a way away from that initial value, which was over 500. Cool. The last thing we'll look at with this is the speed. If you open up the script editor, you'll see that you'll get some information from ZIVA about the speed of the solve. So if I scroll up a bit, you'll see that I was running 4 substeps. I know that because I can see 21.75, so I can tell that that frame's been split up into quarter segments, and you can see the time it took to compute one substep was 0.145 seconds. So we can just remember that number for now. If I go back to the solver start time now, and I change the Z material attributes, if I turn Poisson's ratio to 0, and I set volume conservation to 10, now we have a final value of 10 times 10 to the 6. Now if I play this back, I'll just go through and do 20 frames again. And if I run compute polyset volume on this, you'll see that we have a value of 543 units, which is very, very close, I think, to the original. If I go back to solver start frame, run this again, 545 units cubed. So very, very little volume loss when you're using this method. But you will note that the solve times are a little bit longer. So if I scroll up a bit here, you're going to see here on frame 19 0.75, the wall clock time was 0.34. And previously, when we were just using Poisson's ratio, the solve times were 0.14. And so a fairly significant hit in terms of solver speed, but a much more accurate volume conservation. So just to illustrate it, one more thing, what I'll do is duplicate the object on frame 20. I'll call it frame 20 volume conservation. And then I'll go back to the tissue and change this back. Leave that as it is. Play those 20 frames again. You can see it's much faster. I'll just let it get to frame 20, and then we'll be able to compare the results. So you can see how much more volume is conserved under the volume conservation method. Jump out of there. So the only other attribute in materials to be aware of is density. And density really is pretty self-explanatory, so you can, mess around with this attribute if you want to get different effects. If you wanted to get something like a bowling ball, of course you'd increase the density quite a lot. Or if you're aiming for something like foam in a couch cushion, for instance, you would drop density. So that's really one you can experiment with on your own. Cool, so that concludes the tutorial on materials. As always, thank you very much for watching.